Hi guys, in this video I'll talk about our latest paper about comparing incremental learning strategies for convolutional neural networks. This work was made possible at the University of Bologna as a collaboration between me and my supervisor Davide Maltoni. If you are interested in this line of work, please don't hesitate to contact me through my website vincenzolomonaco.com. So in this short video, I will firstly introduce you to the main problem of using CNNs in an incremental learning context. Then we will define three major incremental learning strategies for CNNs and their possible instantiations that we used during our experimental evaluation. Then we will quickly jump to the definition of our datasets. And the main core of this talk will be about the experiments that we run and the analysis of their results. In the end, we will try to draw some major conclusions about this work and its possible and future extensions. So let's define the problem better. In the last decade, convolutional neural networks have shown to perform incredibly well on many tasks in computer vision, natural language processing, speech recognition. This is because they are very general and adaptive, and specifically because they can work directly on raw data. So we don't need to manually design the features that are required to solve a particular problem. The main problem here is that they are pretty computational demanding and they have a very tricky hyperparameterization. What we don't actually know is their applicability in an incremental learning context. This is because there are very few papers about the use of artificial neural networks and convolutional neural networks in the incremental learning scenario. So let's say that we are in this context where we want to classify different faces belonging to many subjects. And all these images are contained in an initial batch of data, batch 0. And just after some time steps, we can encounter a new batch of data, images of faces belonging to the same subjects. So we call these batches incremental batches. The problem here is that we are subject to stiff constraints in memory. We can afford to keep in memory all the batches all at once, and we are also constrained computationally. We can afford to train our classification model, our prediction model from scratch after each batch. The goal here is still to maximize the accuracy after each batch, but going towards a more smooth and natural way of learning, still using CNNs. So let's see an example. What we would like to do is just to train our model M0 when we have just the images contained on the batch 0 available, and then as soon as a new batch of data, batch 1, is available, we can just update our model M0 to M1 using all these new input patterns. Then we can just remove all the images from the memory, the images contained in batch 0 from the memory, and this is much cheaper than training M1 from the sum of all the images contained in both batch 0 and batch 1. However, this is also dangerous because we risk to forget what we have previously learned about batch 0, sorry. And this is a well-known phenomenon in the literature that is called catastrophic forgetting. Then what we would like to do is just to go on in this process and just remove from the memory both M0 and batch 1 and go on in this way till we end up with a single model Mn that should encode all the knowledge we have extracted from all the images we have seen so far. So the different possibilities that we explored in this kind of context for using CNNs can be conveniently framed in three main strategies. The first one is just training and then tuning an ad hoc CNN architecture that is suitable for the problem. The second one is just using a pre-trained CNN as a fixed feature extractor to be used in conjunction with an incremental classifier. And the third option would be to just fine-tune a pre-trained CNN. So in our experiments, since we focused on image classification, we tested three main instantiations of the aforementioned strategies that are: for the ad hoc architecture, we chose the Linet 7 classical architecture proposed by Jan LeCun in 2004 and still competitive on low medium scale problems. Then for the CNN to be used as a fixed feature extractor with an incremental classifier, we have defined this new strategy, CafeNet plus SVM, that consists of a pre-trained CNN provided in the Cafe library, reference CafeNet, and it is based on a well-known AlexNet architecture trained on the ImageNet dataset. Then for the incremental classifier, we chose the SVM with a linear kernel to be our classifier. So for the third strategy, the CNN pre-trained to be fine-tuned, we have defined this strategy, CafeNet plus FT, where we use again the reference CafeNet model, but instead of using it as a fixed feature extractor, we fine-tune the network, the model, to suit the new task. So furthermore, for the BigBrother dataset that we will introduce and define in a few slides, we designed an additional pair of strategies. For the CNN pre-trained to be used as a fixed feature extractor in conjunction with an incremental classifier, we define this new strategy, VGG phase plus SVM, that is the same as the CafeNet plus SVM, but instead of using the pre-trained model CafeNet, we use this other model pre-trained that is called VGG phased. This is an architecture of 16 levels which has been trained on a very large dataset of faces, like 2.6 million of images. And again, we used in this strategy the linear and incremental SVM as a classifier. So the other one, the VGG phase plus FT, is the same as the CafeNet plus FT, but instead of using CafeNet, we use this pre-trained model VGG phase again, but fine-tuning this model as soon as a new batch of data is available. So for our experimental evaluation, we were interested in datasets where the objects of interest have been acquired in a number of subsequent sessions, where the environmental condition can change among the sessions, like illuminations, backgrounds, and so on and so forth. So we focused on two main applicative fields where incremental learning is very relevant: robotics and biometrics, and chose the datasets respectively. So the first one is the iCub World 28, and the second one is the BigBrother dataset. So the iCub World 28 is a collection of 28 different objects belonging to 7 different classes, and these are domestic objects, very common, like plates or cups, And we have a total number of 39,000 images divided in 9 different training batches and 1 for testing purpose. Each of these image is 128 for 128 pixels, RGB colored. I would like to point out how difficult this task can be, where we have, for example, for the CUPS class, a very low intra-class variation. All these CUPs look very similar to me. For the BigBrother dataset, in this case, this dataset is highly peculiar because we have 7 different subjects, the phases of 7 different subjects that were constrained in a closed environment in a house for 56 days that are the same number of the training batches that are available in this dataset. And we have a total number of 23,000 images, and in this case they are grayscale 70 for 70 pixels wide. Let's bear in mind that also in this case the task is not that obvious to solve because we have for each training data batch a very unbalanced representation of these classes, and also the images can be pretty noisy with distortions and occlusions and very low resolutions and so on and so forth. So let's see the main experiments that we run on these datasets. So for all the experiments we use the same policy. We train all the models until full convergence on the first batch of data, and then we tune them on the subsequent incremental batches, trying to balance the trade-off between the accuracy gain and forgetting. So in this graph you can see the main results for the iCub World 28 dataset, comparing all the strategies that we have defined before. So on the x-axis here, you can see the number of different incremental batches through time, and on the y-axis you can see the level of accuracy that we expect to grow as the number of incremental batches increases. So for each of the strategy here, you can see 2 main lines. The solid one is the actual incremental learning strategy, and the dotted one here, just for benchmarking purpose, is the same CNN, the same model per train or whatever, but retraining the model from scratch after each incremental batch. And so this is not a real incremental strategy. Then the bars for each of the data points indicate the standard deviations among 10 runs in which the order here of the incremental batches is changed, is shuffled. And what we can see here is that the CAFENET plus FT strategy has a very good recognition rate increment, the green lines, and the CAFENET plus FT is the most effective, the red lines. Where the LeNet 7 struggles to learn complex invariant features that are necessary for this problem. I would like to point out also that in this case, for the CAFENET plus FVM and CAFENET plus FT, we have a very low difference between the actual incremental learning strategy and the respective cumulative one, and it is very good since they are very different in terms of computational power and memory that they use, and of course in this case it would be preferable to use the incremental learning strategy. This is not the case, however, for the LeNet 7, where in this case the cumulative strategy is much more better than using the incremental learning alternative. So these are the main results for the BigBrother dataset, and in this case we didn't perform many runs on the same experiment, because what is interesting here is just to see that after 56 days of permanence inside the house, we are able to recognize the phases of these different subjects with a better accuracy. And in this case, the LeanNet 7 model strategy, the black line down here, performs slightly better than the CAFENet plus SVM and the CAFENet plus FT. But what is interesting is that the VGG phase plus SVM and VGG phase plus FT in this case outperform badly the other strategies that have impressive performance on this problem. And this is because they were trained on millions of different phases before. And in the end, the VGG phase plus SVM seems to be the best choice both for the accuracy and stability. The blue line up here. But the most interesting and difficult part of our experiments was dealing with forgetting. In this graph, we can see the same strategy, the CAFENet plus FT, and how a different learning strength encoded as a line, low, and adjustable learning rate can affect the accuracy level through time. So the yellow line here is the CAFENet plus FT strategy with a high learning rate. And we can see that we are subject to a very huge falls in the accuracy. And this is because in many incremental batches, we have an unbalanced representation of the classes, and we have sometimes very different images from the test set. And the red line instead is the same strategy with a low learning rate, and we have a very less noisy line, but in the end we lose some percentage points of accuracy. Our solution in all that we used in all the experiments that we have seen before was to use an adjustable learning rate. And an adjustable learning rate is significantly more stable, the blue line here, and can reach the same level of accuracy as an high learning rate. In this case, we used a simple thresholding approach based on the number of images contained in the incremental batch encountered, and we did not find any significant difference using a continuous approach. So let's now draw some major conclusions. When possible, that is, transfer learning from the same domain, like what we did for the BigBrother case, it is preferable to use CNN as a fixed feature extractor to feed an incremental classifier for stability, essentially. If the features are not optimized, then tuning the low levels of the network may be preferable, and the learning strength can be used to control forgetting, as we have seen in the previous slide. In the end, training a CNN from scratch can be also advantageous, but only if the problem patterns are highly specific and a sufficient number of samples are available. So in the near future, we plan to extend this work by performing, of course, a more extensive experimental evaluation, so with more datasets, and also integrating this comparison with an efficiency comparison, so training times, inference times. Then we would like to find a more principled way of controlling forgetting, adapting the tuning parameters to the size and bias of each incremental batch. And then in the end, we would like to study real-world applications of semi-supervised incremental learning strategies, still using CNNs. For example, we could learn from the first batch of data in a supervised manner and then try to update this model with the incremental batches, but using the temporal coherence as a surrogate signal. So thank you very much for your attention, and if you have any questions about this work or any feedback, please don't hesitate to contact me through an email or through my website, vincenzolomonaco.com.